Hi everyone, Unit 4, Atomic Physics. There are 3 chapters in your textbook that this unit covers, chapters 15, 16, and 17. Okay, so section 1, Atomic Structure, is chapter 15 in your textbook. There's a few curriculum outcomes that I want to draw your attention to. You can read those on your own, but that is all the stuff we're going to be doing this chapter. Okay, a little lower down, you can see that there is a atomic physics pre-assessment as well as 5 parts to this chapter, sorry. Okay, discovery of the electron, quantization of charge, discovery of the nucleus, the Bohr model of the atom, and then a really short one on the quantum model of the atom. Okay, there will be a curriculum review for this section, but no formative assessment. So we'll just look down here for a sec. Okay, so the formative assessment, the atomic physics quiz, and the atomic physics unit exam will cover everything from sections 1, 2, and 3. Okay, and that will all happen at the end of section 3. So you will have you will have a curriculum review for all 3 chapters, but just the one major or one big formative assessment, one quiz, and of course, the unit exam for all 3 sections. Okay, so that's kind of what's going on. So let's flip the page and get started. Part 1, Discovery of the Electron. By 1900, it appeared that all the major theories in physics had been discovered. Almost all the observations in the physical world could be described by pre-1900, so Newtonian or classical physics. Okay? However, a radical revolution was about to take place. This revolution was brought about by a few phenomena that could not be explained by Newtonian physics. This revolution was the beginning of what we now call modern physics. The 3 phenomena that can't be described are relativity, so that's Einstein's big thing, okay, Planck's quantum hypothesis, and atomic structure. So we've already looked briefly at Planck's quantum hypothesis. Quantum theory cannot be explained using classical physics. In this unit, we will be concerned with Planck's hypothesis that energy is not continuous, or that it comes in little packets or chunks, okay, photons. Okay, Planck's quantum hypothesis was the beginning of quantum theory. Okay, we will also show developments in the atomic structure from Dalton to the Bohr model of the atom. Okay, so here we go. So Dalton's atomic theory. Okay, so this really started way back with Democritus. Okay, way back in early. Okay, he was an early Greek philosopher, and he reasoned that matter was composed of tiny particles. Okay, and that's about as far as that went, okay, until about 1810 when John Dalton proposed the atomic theory. During the 18th century, there was a lot of activity in what we now call chemistry. During this time, many chemical laws were discovered, and Dalton proposed the atomic theory as a means of explaining some of these chemical relationships. Okay, so Dalton's atomic theory makes the following statements. Okay, so all matter is consisted of small, indivisible, indestructible particles called atoms. All atoms of a given element are the same. Each element's atomic mass is characteristic for that element. That is, it is different from the mass of every other element. Atoms combine to form compounds, and atoms are neither created or destroyed during a chemical reaction. They're only rearranged. Now, that sounds familiar, doesn't it? Okay. So Dalton's picture or model of the atom was that there were tiny indestructible chunks of matter, so it's called the billiard ball model. Okay, this model had no internal or external features. It was just a ball of stuff. Okay, there were many chemical relationships discovered in the 18th century, which Dalton's atomic theory was successful in explaining. However, we're only going to talk about 3. Okay, so we're going to talk about the law of conservation of matter, the law of definite composition, and the law of multiple proportions. Boom. Okay, so law of conservation of matter. In a chemical reaction, matter is conserved. If all that takes place is a rearrangement of atoms, and atoms are not created or destroyed, then the matter or the atoms are conserved. Okay, so the law of definite composition. A given compound is composed of the same elements in the same proportion by mass. For example, water is always composed of hydrogen and oxygen, and there's always 8 grams of oxygen for every 1 gram of hydrogen. Okay, fair enough. Okay, so definite composition. And then the law of multiple proportions. In a series of compounds formed between the same elements, the mass of one element that combines with a fixed mass of the other element is in a simple whole number ratio. An example of a series of compounds formed between the same two elements, so something like H2O, okay, or H2O2, okay, or NO, so nitrogen oxide, and NO2, which is nitrogen dioxide. It would be difficult to explain these laws without the concepts of atoms. If atoms from different elements combine in the same proportions, and the masses of these elements are always the same, this would account for the law of definite composition. However, if under different conditions, temperature and pressure, these atoms are able to combine in different proportions, it would account for the law of multiple proportions. All right. In the few years that followed Dalton's formulation of atomic theory, chemists were able to determine which substances were elements and which were compounds. They were also able to work out a system of relative atomic mass. They knew that the hydrogen atom is the lightest, and they assigned it the atomic mass of 1. Oxygen atoms were 16 times as heavy, therefore the atomic mass of oxygen was 16. Initially, the standard was hydrogen, atomic mass 1, but it was later changed to oxygen, atomic mass 16, and today it is a particular isotope of carbon, so its atomic mass is 12. Okay, let's talk about the periodic table for a minute. Okay, as more and more elements were discovered, chemists began to search for a pattern that would help them understand chemical properties. Okay, Mendeleev arranged the 63 known elements in order of their increasing atomic weights, okay, atomic mass. He discovered that the chemical properties of these elements were repeated on a regular basis. Therefore, the name periodic table was used. He further arranged the elements that had the same chemical properties into columns. By doing this, he discovered there were some blank spaces in the table. Some elements appeared to be missing. He was able to reason that the blank spaces represented elements that had not been discovered. He was able to predict the chemical properties of these yet undiscovered elements. Okay, if you look at the periodic table, the elements in the same column have the same chemical properties. The chemical properties repeat on a periodic basis. It should be noted that in the periodic table today, the elements are listed in order of increasing atomic number, which of course is the number of protons in them, rather than their atomic mass. Okay, however, there are very few differences in the arrangement, okay, flip the page, of the elements when they are listed in order of increasing atomic numbers rather than increasing atomic masses. Okay, there are questions that the Dalton model, or the billiard ball model, had difficulty answering. It was these questions that first suggested that the simple view, billiard ball model, needed to be amended. The questions that Dalton's model had trouble with were, okay, how do atoms combine to form compounds? Okay, what holds them together? How do we account for the repetition of chemical properties in the periodic table? Sure, Dalton was great at figuring out, or Dalton's model rather, that, 2 hydrogens for every 1 oxygen, or like that kind of thing. But what held the oxygen and the hydrogen together? That was weird. Okay? And then why does the periodic table, why do the chemical properties repeat? There's got to be something there. Now, we of course know today that there's like electrons floating around and stuff, but they didn't know that back then. Okay. So both of these questions suggested that there was some internal structure to the atom. It may not be as simple as the billiard ball. Well, he had no idea, because you guys, even with the stuff you've taken already, know that there's more going on inside an atom than just a ball. Okay, so let's talk about something called cathode rays. Okay, so with the invention of highly efficient vacuum pumps in the middle of the 19th century by Giesler, okay, scientists began investigations that led to the discovery of the electron. Scientists were able to investigate the electric discharge across a spark gap in a vacuum, or in gases at very, very low pressure. Okay, when electric discharge takes place in a gas under low pressure, the gas will glow. Okay, different gases produce different colors. Okay, tubes containing gases under low pressure can be called discharge tubes. Okay, we use discharge tubes in spectrum analysis. These discharge tubes are known by a number of names. but the name we're going to use is a cathode ray tube, or a CRT. Okay, so the idea of a cathode ray tube, here's a picture of one. Okay, so we have this, it's almost like a fluorescent light. Okay, it's got gas under low pressure, so if you break it, it pops. Okay, makes that sound. Okay, now you connect, okay, so it's got two wire leads coming out of the sealed unit. Okay, one's called cathode, one's called an anode. Okay, and we attach those to the high voltage power source, basically. Okay, so we have to have a high voltage potential difference. Okay, awesome. Okay, the term cathode ray is used because it was determined that the discharge originated at the negative electrode, or the cathode. This was determined because the tube glowed with greater intensity opposite the cathode, as indicated in the diagram below. Okay, so what they did is they took a bent tube, okay, a bent vacuum tube, okay, again, hooked up the anode and the cathode, and they figured out that, oh, it glowed more on this side, so they figured out that, hey, wait a sec, these things have to be coming from the cathode. Okay, that's why it's called cathode ray tubes, not anode ray tubes. Does that make sense? Okay, coming from the cathode. Awesome. Okay, over the next few years, okay, scientists discovered different properties about the discharge that became known as the cathode ray. These properties were, okay, cathode rays travel in straight lines. Cathode rays might be considered to be moving particles. They can be deflected by magnetic fields. They can be deflected by electric fields. Okay, it never mattered what the cathode was made of, silver, gold, copper. It didn't seem to matter, but the properties of all the cathode rays that came out of those metals, they were always the same. Okay, and cathode rays can produce chemical reactions similar to those of light. Okay, so kind of interesting. Okay, at first it was speculated that cathode rays were some form of EMR. Remember that cathode rays were discovered shortly after Hertz demonstrated that EMR existed. Okay, however, cathode rays do have some of the properties of EMR, some of the properties of light. Okay, they both travel in straight lines, they both bring about chemical change. However, cathode rays have extra properties that EMR or light doesn't have. Okay, for instance, cathode rays can be deflected by electric and magnetic fields. Okay, EMR can't. Okay, we know now that EMR can't because EMR doesn't have a charge. Okay, these cathode rays definitely had a charge. Okay, there are a number of scientists that study cathode rays, but two names that you should remember are Crookes and J.J. Thomson. Crookes discovered many of the properties that we listed above, while J.J. Thomson is given credit for discovering the electron through experimenting with cathode ray tubes. Okay, Crookes speculated that cathode rays might be particles, which J.J. Thomson proved was correct. In addition to finding the electron, Thomson also determined its characteristic charge to mass ratio. So Q divided by M. Remember, Q is charge, M is mass. So he figured out the charge to mass ratio. Okay, a value for an electron would be 1.76 times 10 to the 11th coulombs per kilogram. Okay, so that's using the standard 1.60 times 10 to the negative 19 coulombs divided by 9.11 times 10 to the negative 31 kilograms. Okay, now the experiment used by J.J. Thomson to measure this charge to mass ratio is described on the next page in the following paragraphs. Okay, so have a look at the Thomson experiment. Okay, so he used this cathode ray tube, kind of weirdly shaped, but whatever. Okay, he had this built-in kind of circular anode. Okay, so basically if you look at it from the front, it looked like that. Okay, so you turn it sideways, you get that. There's a hole in the middle. Okay, awesome. All right, so in this experiment, cathode rays passed through a magnetic field, which was found to deflect the rays. Okay, the anode is a circular disc with a hole in it through which electrons are accelerated from the cathode. Okay, this part can be called the electron gun or accelerator. Under high voltage, the electrons have high kinetic energy or high speed when they reach the anode. Once the high energy electrons pass through the hole, then they pass through a magnetic field where they are deflected up or down. As this deflection is in an arc or part of a circle, the net force causing it is a centripetal force. Okay, now we've seen stuff like this before. Okay, when you pass these particles through it, well, it happens with an electric field or a magnetic field. Okay, we get this circular path. Now, as soon as you mention the word circle or circular path, we think of the centripetal force. Now, remember that force is not on your formula sheet. You have to know that F equals ma, and if we're talking about a centripetal force, we have to talk about a centripetal acceleration. Now, on your formula sheet, your centripetal acceleration is v squared over r, so that's where the, okay, so if we substitute that in, so it's mv squared over r, okay, so that is where this formula comes from, and you have to know how to make it. All right. Okay, so mass, of course, in kilograms, v is meters per second, r is the radius of the arc measured in meters, so if it's given to us in another unit, we have to convert, and of course, Fc is the magnitude of the centripetal force. Okay, so I gave you the little explanation down below on how to find that. Okay, awesome. Okay, so that takes us to about here. Okay, in this case, the force causing the electrons to deflect is the magnetic force. So we say the centripetal force equals the magnetic force. So mv squared over r equals qvb. Okay, lastly, we cancel a v from both sides. See how that v squared, the squared cancels with one of those. Okay, so we end up with mv over r equals qb. Okay, and then what we do is we want the charge to mass ratio, so that's Q over M. Okay, that's what Thomson found. So if we do that, the M has to come down to this side. Okay, so that gives us Q over M. Okay, and then the B divides this side, so we end up with the V over BR or RB. Order doesn't matter. So there is the charge to mass ratio and how he solved it. Okay, the charge to mass ratio that Thomson measured is the Q divided by M from that formula. The R and the B can be measured directly. However, okay, we can't measure the speed of the electron. It's going way too fast. Okay, so we had to do something different, or pardon me, there's no we about any of this. Thomson had to do something different. Okay, so what he did is, knowing with all the electrics we've done and everything, okay, you can figure out the change in energy of an accelerating electron. Okay, so that is delta E equals delta V equals E over Q. So we've seen that formula before. So we usually rearrange it to energy is voltage times charge. Okay, and then EK is 1/2 mv squared. Okay, so this part here is 1/2 mv squared. So equals VQ. Okay, now here's the funny thing though. To use either of these equations, okay, both the mass, the M right there, and the charge, the Q right there, are required. Thomson didn't have either. Now, of course, we know them now, right? We know the mass of an electron, we know the charge of an electron, but he didn't. Okay, so he had to find the speed by passing the electrons through a magnetic and an electric field at the same time. Okay, the electric field and the magnetic field were adjusted so that the electric and magnetic forces acting on these electrons were equal but in opposite directions. In this case, the electrons travel in a straight line with no deflection. Okay, so if you put an electric field or a magnetic field here, an electric field there, okay, and adjust them appropriately, okay, instead of the electron curving, it just goes straight. Now, if the electric field is stronger, it curves one way. The magnetic field is stronger, it curves the other way. So in that sense, only the particles that went straight through could actually do the experiment. Okay, so Thomson was able to measure the velocity that way. Okay, so how he did that, Fe equals Fm. Okay, now remember, Fe is just E Q. Now I have that written here, but let's just write it out. So Fe equals Fm. So Fe is the electric field times the charge. Okay, Fm is Q times the velocity times the magnetic field. Now if you look at those, hey, the Q's cancel. Okay, so if I want the velocity of these electrons, okay, I just divide by B, and the velocity of my electrons is the electric field divided by the magnetic field. Okay, awesome. So there's a nice little derivation of that formula there. It is not on your formula sheet. You just have to know how to do it. Okay, remember, so much of Physics 30 is equating or balancing forces. So Fe equals Fm. Start there, and away we go. Okay, so Thomson obtained the speed of the electron as the ratio of the field strengths. Now that he had that speed, now we could come back to the charge to mass ratio, because he now has the speed. He could measure the magnetic field, and he could measure the radius. Okay, so once we have all those things, okay, so now we could figure out the charge to mass ratio. So that was that number that we talked about from this page, right at the bottom. No, not there. Sorry, my bad. Anyways, okay, but now once he had that, he could figure out the charge to mass ratio. Awesome. All right, so let's look at some of the problems that you're going to get with stuff like this. Okay, so really, these are going to be about finding the velocity or finding the charge to mass ratio for all these things. It's really not that big a deal, so just bear with me. Okay, so practice problems number 1. Charged particles are traveling horizontally at 3.60 times 10 to the 6 meters per second when they enter a vertical magnetic field of 0.710 teslas. If the radius of the arc of the deflecting particles is that, what is the charge to mass ratio of the particles? Okay, so we know we have a magnetic field, so that means we have a magnetic force. Okay, we have a radius, which means we have a centripetal force. Okay, so we go Fm equals Fc. All right, great. Okay, Fm, of course, is QVB, and Fc is mv squared over r. Okay, remember, we cancel off one of the velocities. Okay, so that's great. Now, once that happens, okay, we want the charge to mass ratio of these particular particles. Okay, so charge to mass is charge, or Q, divided by m. So we have to rearrange the formulas, okay, to get Q divided by m. So if we look at that, the m divides down and the b divides down. So then I end up with Q over m equals V over BR. Now remember, right, one of those velocities canceled. That's why it's not V squared anymore. Okay, so once I have that adjusted formula, now I just put in the numbers. So my velocity, 3.60 times 10 to the 6 meters per second. Sorry, I know I'm a little cramped there, guys. Hopefully you can tell where it is I'm writing. Okay, there we go. 3.60 times 10 to the 6th meters per second divided by 0.710 teslas. Okay, and then the arc, the radius is 9.50 times 10 to the negative 2 meters. Okay, awesome. So make sure you put the bottom in brackets or use a fraction template depending on your calculator. Anyways, when we figure these ones out, it works out to 5.34 times 10 to the 7 coulombs per kilogram. So definitely not the electron, but that's okay. Okay, great. Number 2, what is the speed of an electron that passes through an electric field of that and a magnetic field of that undeflected? Assume the electric and magnetic fields are perpendicular to each other. That's how these things work, right? They have to be perpendicular so that the forces are going in the opposite direction. Okay, so if the electron passes undeflected, it must mean that the two forces are the same. So FQ, wow. So Fe equals Fm. Okay, so Fe, remember, is the electric field times the charge. The Fm is Q times V times B. Okay, oh look, there's a Q on each side, so it cancels off. Okay, and then we divide by the B, divide by the B. So our velocity is the electric field divided by the magnetic field. Okay, so typing that in, so the electric field 6.30 times 10 to the 3 newtons per coulomb. Okay, and then the magnetic field 7.11 times 10 to the negative 3 Teslas. Okay, so when we type those into our fancy calculators, we end up with our velocity of being 8.86 times 10 to the 5 meters per second. Okay, we got 3 sig digs. We round, yep, okay, and there you have it. Awesome. Okay, then the third question here. Okay, an electron traveling vertically enters a horizontal magnetic field of that. If the electron is deflected in an arc of radius that, what is the kinetic energy of the electron? Ooh. So remember, kinetic energy is EK, and that's 1/2 mv squared. So we have the mass of the electron, so that's no big deal. We don't have to pretend that we're J.J. Thomson and don't have it. Okay, no, that's not how we do things. Okay, so we want the kinetic energy. So really, this question has to be telling us how to solve for velocity. And of course it does, because we know that we are going into a horizontal magnetic field. So that's it. As soon as we have that, we have an Fm. And as soon as we see the word arc, we know that there is an Fc. Okay, so that must help us to find velocity, and of course it does. So Fm is qvb, Fc is mv squared over r. Remembering there is a v on top on both equations, that's why it cancels. Okay, so this time I want the velocity. Okay, so the velocity is right there. Okay, so the r multiplies up, the m divides down. So my velocity is q. Okay, the r went up, so qbr, and the m came down. Okay, so there's our velocity. So the q of an electron is 1.60 times 10 to the negative 19 coulombs. The magnetic field we're going through, 7.20 times 10 to the negative 2 Teslas. Okay, the radius, 3.70 times 10 to the negative 3 meters. Okay, and then the mass, of course, 9.11 times 10 to the negative 31 kilograms. Okay, so when we figure out the velocity here, we get 4.68 times 10 to the 7th meters per second. So once we have that speed, now we can go back up to the EK. Here, I'm going to just, okay, so EK is 1/2 mv squared. So that's going to be 1/2, 9.11 times 10 to the negative 31 kilograms. Okay, times 4.68 times 10 to the 7th meters per second. Sorry, kind of running out of room there. Squared. Don't forget to square that velocity. Sorry, guys. Hopefully you have more space. Okay. Now, when you type that in, you end up with 9.97 times 10 to the negative 16 joules. I know that doesn't seem like a lot of energy, but to something as big as an electron, that is huge. Okay, awesome. So there is section 1. I'd like you to practice this stuff by looking at page 760 in your textbook. You can use your textbook, or remember, I've made cards in your workspace for this, so you can print it off if you want, and then write your answers right on the question booklet. Okay, doesn't matter to me, whichever one you want, and I will see you guys next section. Thanks.